Welcome to this explainer. Today, we're diving into a true landmark paper that proved a fundamental point in deep learning. You don't just need to get bigger, you need to get smarter. We're unpacking, going deeper with convolutions, the massive research breakthrough that introduced the world to the Inception architecture and its absolute superstar incarnation, GoogleNet.
Okay, here's our roadmap for today. We'll cover Section 1, the deep learning bottleneck, Section 2, the Inception module, Section 3, the one-by-one convolution secret, Section 4, meet GoogleNet, and finally, Section 5, crushing the competition. Let's jump right in.
Section 1, the deep learning bottleneck. Why bigger isn't always better. To really appreciate this breakthrough, we first need to understand the brick wall that AI researchers had hit. See, the standard way to improve neural networks was simply to make them larger. Add more levels of depth or increase the width by slapping on more units at each level. It's safe, and it works, sure, but that brute force approach came with some major structural drawbacks.
Imagine trying to teach a machine to spot incredibly fine-grained, expert-level differences in images. It requires an insane level of complexity. The challenge is, as you scale up the size of these networks to handle that kind of complexity, you dramatically increase the number of parameters you're dealing with.
Just look at the two dogs on the screen right now. Telling a Siberian Husky apart from an Eskimo dog requires massive network capacity. But if you just uniformly pump up the number of filters in your network to handle these tiny, fine-grained differences, the required computation scales up quadratically. If those extra weights just end up sitting close to zero, well, you've just wasted a massive amount of your computing power. So the really crucial point here is that mindlessly inflating a network is a trap, and not only wastes your finite computing budget, but it also leads straight to overfitting, especially when your high-quality training data is limited. The researchers realized they needed a fundamental shift. They had to move from fully connected architectures to sparsely connected ones.
Moving right along to Section 2, the Inception module, a smarter way to build. To solve this crazy bottleneck, researchers engineered a brilliant workaround. They built a new, local sparse structure they called the Inception architecture. Basically, they wanted to figure out how an optimal, local sparse structure could be approximated using the dense components they already had readily available.
Now, what's genuinely fun about this is the pop culture hook. The researchers literally named their groundbreaking architecture after the "we need to go deeper" internet meme from the movie Inception. They knew, for sure, they had to go deeper, both in terms of actual network layers and in discovering a whole new level of organization. To actually build this thing, they looked to biology and math for inspiration, specifically the Hebbian principle. You might know it as the idea that neurons that fire together wire together. Their goal was to analyze the correlation statistics of the previous layer and basically cluster highly correlated units together into efficient groups.
So here is what they called the naive version of their idea. Because visual data needs to be processed at various scales all at the exact same time, this module just stacks 1x1, 3x3, and 5x5 convolutions side by side. It processes the input image region through all of these filters simultaneously, concatenates the outputs into a single vector for the next stage, and even throws in a parallel max pooling path for good measure.
But hold on a second, what happens to the math here? The glaring problem with this naive setup is that merging the outputs of all these pooling and convolutional layers leads to a completely prohibitive computational blowup. Even just a modest number of 5x5 convolutions can literally melt your servers if they're sitting on top of a layer that already has a large number of filters.
Which brings us to Section 3, the one-by-one convolution secret, compressing the data. This right here is the secret weapon that made the entire architecture possible without triggering a catastrophic computational failure. They desperately needed a way to keep the representation sparse where it actually mattered, but compress the signals whenever they had to be aggregated en masse.
Think of it kind of like zipping a massive file before you try to send it through a really tight pipe. They introduced one-by-one convolutions purely as dimension reduction modules. By applying these reductions before they hit the computationally expensive 3x3 and 5x5 convolutions, they could safely shrink the data down first. Now take a look at the new yellow blocks strategically placed in this updated module. Those one-by-one convolutions compute the reductions, keeping the network sparse and keeping those computational budgets strictly in check. Plus, they included rectified linear activation, making them completely dual-purpose, which is just super clever.
So the massive takeaway here is that these Inception modules allowed the team to vastly increase the size and representational power of the network, but without the usual crushing performance penalties. It captures multi-scale features seamlessly, and incredibly, it allows for networks that are 2 to 3 times faster than similarly performing non-Inception architectures. All right, Section 4, meet GoogleNet, the 2014 ILSVRC submission. Now we get to take those individual Inception modules we just walked through and we stack them up to see the final monstrous architecture they built for the big ImageNet competition. Okay, I know this looks super intimidating on screen, but you're actually looking at an absolute masterclass in efficiency. They named this specific incarnation GoogleNet, which is a great little homage to Jan LeCun's pioneering LeNet 5 network. Just notice how the Inception modules are stacked one right after another, creating this towering, highly optimized structure.
22. That is the staggering number of parameter layers this network goes deep. If you count the pooling layers, it's actually 27. It was an absolute marvel for its time, designed with such computational efficiency that it could theoretically run on individual devices with limited resources and really low memory footprints.
Of course, to make a 22-layer beast actually train effectively, they had to rely on some very clever engineering tricks. One huge problem with deep networks is that the gradient signal, the actual learning signal, can just fade out before it ever reaches the early layers. To fix that, they attached intermediate auxiliary classifiers directly to the middle layers, pushing strong gradient signals back through the network. They also swapped out traditional fully connected layers for average pooling, which surprisingly improved top 1 accuracy by 0.6%, and they kept the entire inference budget to just 1.5 billion multiply adds.
Let's look at the payoff in Section 5, crushing the competition. The ILSVRC 2014 results. Theory is great, but what actually happens when GoogleNet gets put to the ultimate test against the best models in the entire world?
The ImageNet challenge was the ultimate proving ground for computer vision back then, and the task was just brutal. Classify 1.2 million training images into 1,000 highly specific categories, like distinguishing all those different dog breeds we saw earlier. The team entered using an ensemble of 7 trained GoogleNet models, and remarkably, they did it using absolutely zero external training data.
This graph pretty much says it all. GoogleNet hit a stunning 6.67% top 5 error rate. Just to put that into perspective for you, that represents a massive 56.5% relative reduction compared to the 2012 winner and about a 40% reduction compared to the best approach from 2013. They took first place handily. But wait, it wasn't just classification. When they applied GoogleNet to the object detection challenge, using an approach similar to RCNN but augmented with their Inception model, they absolutely dominated. They took first place again, achieving a 43.9% mean average precision, which almost completely doubled the accuracy of the prior year's winner. And honestly, the most remarkable part of this entire explainer, GoogleNet achieved this world-beating, state-of-the-art accuracy while using 12 times fewer parameters than the winning architecture from just 2 years prior. They got vastly superior results not by using brute force computation, but by utilizing their computing resources with unprecedented efficiency. This landmark paper proved, once and for all, that a smarter, structured design absolutely beats sheer brute force. By moving towards sparser architectures, they unlocked a whole new paradigm in computer vision. It leaves us with a thrilling question to end on. If we can automate the construction of these sparse structures, what kind of incredible network topologies might we uncover next? Thanks for joining me on this deep dive into the Inception architecture.